Okay, so far we've been talking about explicit equations. These are functions. You plug in one x, you get one y. But a lot of things in the universe can't be graphed by functions, but graphed by implicit equations, where you can't just plug in any x and get a y. You have to plug in select combinations of x and y's to satisfy this equation. Okay, we are going to be looking at these graphs of these equations. Okay, this guy, the first guy, is a circle. We'll be looking at ellipses. We'll be looking at things in the back of our throats. Okay, we'll be looking at things that look like fishes for a specific part of the graph. Okay, ovals. Okay, all these things, they have tangent slopes too. Okay, they not only have horizontal tangent slopes, but some of them have vertical tangent slopes. Okay, so we are going to be analyzing these implicit equations, these non-functions, and we will find some interesting situations, locations, and equations of tangents to these functions. Okay, you won't have to worry about graphing them, so don't worry about that. Just worry about taking the derivatives and finding dy dx, and that's what we're doing. If I am asking you to take the derivative of this function, what are we finding? Well, I take the derivative of y, I get y prime, but we're going to say that's dy dx. I'll show you why in a second. And that's equal to 2x plus 2. Okay, we are finding dy dx. That's instantaneous change of y over instantaneous change in x. Change in y over change in x. Rise over run. That's slope. But since it's an instantaneous change in y over instantaneous change in x, we've been finding tangent slope. Okay? We need to do that for this. What's dy dx for this guy? Okay? Well, we'll get there in a little bit. Okay? Now, let's look at derivatives of these y's. And we know that the derivative of y is y prime, but I'm going to use dy dx strictly today. And why we can see that is, if you use kind of multiplication, I could take this derivative times y and this dx times 1, and you can see you get this dy dx. Right? Kind of just multiplication. Well, for these other ones, I'm going to treat them like chains, like compositions. I'm going to put that y in parentheses. I'm going to say this is an outside, which is some stuff being squared, and an inside, which is the y. Well, if I took the derivatives of those with respect to x, we say that the derivative of this outside is 2, stuff to the first power, and the derivative of the inside, well, I just talked about the derivative of y was dy dx. So I'm going to put dy dx. Remember, when we're taking the derivative of a chain, we'd multiply these two together. So I'd end up with 2y dy dx. Let me do the other one. 3y to the 4th. I'd consider it an outside, which is the 3 stuff to the 4th, and an inside, which is the y. Derivative of the outside would be 12 stuff cubed. Derivative of the inside would be dy dx. So I would say this is 12y cubed times dy dx. This guy, well, outside is 6 stuff, inside is the y. Now, if I thought of this as 6x, the derivative of 6x is just 6. I'm going to say this is just 6. But the derivative of y is dy dx. Now, what we notice is that taking derivatives of these y's is the exact same thing as taking the derivatives of the x's, except we need to multiply our kind of finished product with a dy dx. Same as derivatives of x's times a dy dx on the end. I don't know why I didn't put a 6 over here. Was that your question? Okay. So, moving forward, you do not have to use this chain rule process. Instead, you could just think of them as having x's, take the derivative of them as having x's, and then just make sure you include a times dy dx on the end. Understanding this whole chain rule process, which creates this need to have a dy dx on the end. Take the derivatives of these three, and then look up on the board and make sure you got them correctly. And be careful with the second one, but again, treat it like you have x's. You know you have to use the chain rule if you have the x's on sine of x cubed. Take the derivative of it, include a dy dx on the end. Okay, check your answers with the board. Any questions about these? All right, good. Now, if we looked at, go back to the derivative of like x squared, or just the derivative of x. We said the derivative of x was just 1, right? Well, watch how this notation works out. You kind of multiply that d by the x and multiply the dx by the 1. You get dx over dx, right? Well, that's just 1. So really, for this one, you could say this was 2x times dx over dx if you consider this as an outside and an inside. But we don't have to do that because this is just equal to 1. So we just excluded it. But if I had the derivative of like z squared, we would need a dz dx. Using that multiplication, right? Outside squared, inside z, taking the derivative with respect to x of z, d times z dx times 1, dz dx. We will be seeing next class, we're going to be taking the derivatives of these variables with respect to t, and we're going to have all sorts of dx dt's, dy dt's, dz dt's, dr dt's, okay? We'll see that next class. Today, just dy dt's, dy dx's that we're going to be seeing, okay? Now, we can have x's and y's together. Just don't forget your rules still apply when you have x's times y's. Okay, first one, piece of cake, the derivative of y squared, 2y dy dx, plus x squared, 2x, and that's it. But where students make mistakes is where we see products of x's and y's. They forget to use the product rule. Okay, so make sure we use the product rule for x squared y cubed. Derivative of the first piece times the second. Notice, I don't have a dy dx on the first piece. This is derivative times the second, because the first piece is just x squared, its derivative is 2x, times the second piece, y cubed. It's when I'm taking the derivative of the second piece, when I get 3y squared, that I would need my dy dx there, times x squared. Okay, just the product rule. So go ahead and take the derivative of xy using the product rule. Okay, we'd get 1 times y plus dy dx times x. And then, of course, the quotient rule as well applies. Derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. Okay. Now, moving on, we need to be careful when we have, like, subtraction signs in front of product rules. There are 2 ways that I like to handle this subtraction sign, okay? I'll show you both ways, and it really depends on the situation what I like to do, but I either bake in or leave out. What do I mean by bake the minus in? I mean rewrite this so that it's x squared plus a negative xy plus y squared. Now, taking the derivative of this, we can see that negative sign would be baked into the x times the y when I'm using the product rule. I'd get 2x plus negative 1y plus dy dx times negative x plus 2y dy dx. We end up with 2 dy dx's in this product. Okay, and just make sure you know that this is times negative x, not minus x. It's very important to see that. The other way to do it is just to leave it out. So leave it as x squared minus. I'd probably just understand that this is x times y in parentheses. And I would take the derivative of everything, giving me 2x and then minus the quantity of the derivative of x times y. So this would give me the 1 times y plus dy dx times x, and I would go from there. And then you can see you would then be able to distribute that negative sign to the y and to the dy dx x. Okay? Key is to just be careful as you're doing it. So go ahead, and if you have space, take the derivative of this, pick a method, go with it. Either leave that minus out in front of the 3xy, or bake it in and make it a negative 3x. Horrible star. Okay, I baked it in when I did it. You can look at your derivative of that expression once you're done. Okay, derivative of negative 3x is negative 3 times y plus the derivative of y dy dx times negative 3x. Questions about that? All right, we are ready to now find dy dx for an implicit equation like x squared plus y squared equals 9. Okay, again, that's our goal. Find this tangent slope generator, which is dy dx. That's probably an important thing to write here. This is a tangent slope. Not only is it a tangent slope, but when we find an equation, we get a tangent slope generator. We plug in x's, you get tangent slopes. Okay, let's see what it will look like for x squared plus y squared equals 9. Now, here's the procedure. But it's really simple. First step is just to take the derivative. You can consolidate the second step to just be algebraically solve for dy dx. It won't pop up as nicely as it did. Now, consistently, what we will end up doing is collecting all terms of dy dx on one side, move the other terms to the other side, factor out a dy dx, and divide. I'll show you what that looks like, maybe not for this one, but for the next one, okay? So here, find what this tangent slope generator is. I'm going to take the derivative of the entire thing, just like I did with y equals something. But in this case, when I take the derivative of this thing, I get 2x plus derivative of y squared 2y dy dx. And then don't forget that the derivative of 9, we need to take that derivative. This is 0. Don't forget that. Okay, we're taking the derivative of everything. The derivative of a constant is 0. Okay, well now I need to find dy dx. Well, dy dx is right here. I can algebraically solve for dy dx. What does that look like? Well, go ahead and get rid of this 2x, which is being added to it, by subtracting it. This is a term without a dy dx. Move it to the other side. What should I do now? Well, go ahead and divide by 2y, because it's being multiplied by dy dx. If you'd like to, you can cancel these 2's, because we're not adding anything here. And we've just discovered what dy dx is equal to. Okay? This is our tangent slope generator for x squared plus y squared equals 9. In this case, we would be plugging in x, y's, because we need an x and a y. We'd plug in x, y points that work in our original equation, that are on the graph of our original equation, into this. Okay, so an example. Somebody give me a point, x, y, that satisfies that equation, x squared plus y squared equals 9. 3, 0, right? Always a popular one. So I could do dy dx at 3, 0. We would kind of denote it like that. I'd plug in 3 and 0 for x and y. Now I get a dy dx that's negative 3 over 0. That's undefined, right? But what does that type of undefined tangent slope look like? It's a vertical line. Very nice, Miss Hathaway. So this is a vertical tangent. Let's look at the graph of x squared plus y squared equals 9. X squared plus y squared equals 9 at 3, 0. Sketch a tangent slope right there. What do we see? It's vertical. Okay, I could plug in a value like 2 root 5. I'd get negative 2 over root 5. That's close to negative a half. Well, look, at the point 2, this must be the y-coordinate of root 5. I can see the tangent slope there appears to be that negative 1/2. Okay, so that is my tangent slope generator. I'd plug in points on the graph of this circle, and I'd find the tangent slopes. Fantastic. That one was easy. Very simple. Let's do something a little bit more difficult, like this one. X squared minus xy plus y squared equals 10. Go ahead and let's take the derivative and let's make sure our first step is correct before we do anything crazy. Maybe this time you want to leave things out. It's up to you. Should have told me. Okay, is everybody good with that first step? Now, if you baked in that negative, you'd have this negative 1x, negative 1y, and then you'd have a negative x there. Okay, whatever. Now notice we have two dy dx terms here. This dy dx negative x and this 2y dy dx. Also, be careful to draw and write your x's and y's neatly so you don't confuse a y with an x. Okay, I'm not showing a good example of that. There are two terms without a dy dx right here. Let's go ahead and just get those out of there. Subtract 2x and add a y. Okay, good. Now, I need to solve for dy dx, but I have two of them. What do? I factor out a dy dx. And you'd end up with negative x plus 2y times dy dx. Now, the last step would be to divide by what dy dx is being multiplied by to just get dy dx by itself. Go ahead and divide this by negative x plus 2y. And divide this by negative x plus 2y. And you've just found dy dx. Now, if I had a point that satisfied this implicit equation, this is the equation of an ellipse, I'd be able to plug that point into this to find its tangent slope, the x's and the y's. Okay, let's go ahead and try another one. You guys can try this by yourselves. Look up to see if your answer is correct. There is my tangent slope generator for that implicit equation. Questions? Okay, let's flip over. We can find locations of horizontal and vertical tangents. And before we just start jumping into this one, let's talk about horizontal tangents and vertical tangents. I'll use h dot t dot to signify a horizontal tangent. Okay? That's when my slope is equal to 0, right? Well, you can also think of a 0 as being a 0 over a number. It's still 0, right? Okay, good. Our vertical tangents occur when what, Miss Hathaway? When it's a number over 0, exactly. Just like in that location 3, 0 on the graph of x squared plus y squared equals 9. Okay, so keep that in mind. Because when we take our derivative and find dy dx, we typically end up with a fraction. And we'll be able to use that fraction to find our horizontal and our vertical tangents. Let's go ahead and find dy dx for this one. And look up on the board and make sure you get the correct dy dx. Go for it.
You show how you still get the dy dx to the negative sharp line.
Right, so think of it as 5x. What's the derivative of 5x? 5, right? Well, the derivative of 5y would be 5 times dy dx.
No matter what.
No matter what it is. If it's a y, you're going to need a dy dx at the end. Okay? Then, add 2x. Factor out the dy dx. Divide to solve for dy dx. Okay? We start with that. Now, finding my horizontal tangents. When dy dx is a number over, or sorry, a 0 over a number. I'm going to set this equal to 0. Or think of it as 0 over a number. All that we care about is the numerator being equal to 0. And as long as my denominator is not equal to 0 at whatever this value is, then I'm fine. Well, I get x equals 0. I will have a horizontal tangent. Now, if you want to find the points, you'd have to take this point, x equals 0, plug it in, and solve for y. In this equation, it's not easily solvable for. You'd have to use your calculator to find it. So in some of these questions, you're just going to be asked to find the x location or the y location, not the xy points. So you just stop right there, and that's fine. Now let's talk about the vertical tangents. That's when we have a number over 0, so I just need to set my denominator equal to 0. And I get 2 y coordinates. Now I can plug those in and actually easily find x squared. It would be a little bit of work to do all the arithmetic, but it is possible. Now what's great is to look at the graph of this. This is actually the equation for the thing at the back of your throat. There it is right there. Okay? That's the equation for it. When x is 0, I only have one point when x is 0. Notice, horizontal tangent there. When y is -5, when y is -5, I have 2 points, this x and this x. Well, notice, vertical tangent here, vertical tangent here. When y is 1, vertical tangent here, vertical tangent there. Okay? So we did it. We found it just by using some calculus, some derivative rules, solving for dy dx. Okay? Next one. We can write equations of tangent lines. No big deal. The only difference between the equations now and the equations from like Unit 2 and Unit 3 is that they have to give you the point. They can't just give you x equals 1. Because if I plugged in x equals 1, there may be 2 y's for that x. So it actually make it easier for you by telling you the exact location that we're looking for, the exact point on the graph of this. Okay? All we need to do is find m in our equation y minus y1 equals m times x minus x1. So what goes there? Whatever my dy dx is at 1, -3. Go ahead and find the equation for dy dx and plug in 1, -3. Either bake in that minus sign into that 3 or leave it out but use parentheses. Probably in this situation, I would bake it into the 3 and make this plus a -3. But that's just me. You could do it different ways if you'd like to. We have a product, use the product rule. Simple. Now all we have to do is find this at 1, -3. Okay? Do the next one. Now, pause after you write down your first step and make sure your first step is correct. Do you have this guy? Remember the derivative of cos 2y. We have the cosine of, and then the 2y. Derivative of cosine negative sine. Derivative of 2y, 2 dy dx. That's where that 2 comes from. From the derivative of the inside of cos of 2y. This would be the cos of 2y. You have an outside and an inside. Outside is negative sine. Inside is 2 dy dx. So I have negative sine 2y times 2 dy dx. Okay? Solve for dy dx. Great. We have our point, so we have the y1 and the x1. Now I just need my tangent slope at this point. Typically, it's nice to write like the point that you're plugging in right underneath the dy dx. That way you just like know, and make sure you plug in the x's for the x's and the y's for the y's. If you want to get rid of the negatives, you can. It's not necessary. Okay? Make sure you plug in the point. I see a lot of students still make the mistake of like taking this entire dy dx and using that for m. No, that's not going to be an equation of a line anymore. It would be some crazy implicit equation. Okay? Now, sometimes they will ask you for the x, y locations of your horizontal and your vertical tangents. Now, you could find both of them. Just to make this a little bit shorter, let's just go ahead and find the x, y locations of our vertical tangents. And we'll skip the horizontal, but it'll be the same procedure. Okay? Vertical tangents, your dy dx is going to be some number over 0. So we just need to set the denominator of our fraction equal to 0. Let's go ahead and find dy dx here. Okay, for my vertical tangents, set the denominator equal to 0. Great, I have the y locations, but I want the xy locations. What would I do here to find the x locations when y is negative 2? Exactly, take this Plug it into the equation that tells us the relationship between the x's and y's for all of these points on the graph. Okay, go ahead and do that. Let's see what the x locations are. Okay, we get 0, -2, and 2, -2. Let's look at the graph of this guy. 0, -2, vertical tangent. 2, -2, vertical tangent. Awesome. We just did that. Okay. Make sure you list your x, y points as x, comma, y. Okay, so don't find y first and then list that first. The x coordinate is 0. The x coordinate is 2. Okay, it'd be the same thing if I want to find my horizontal tangents. I'd set that equal to 0. I'd get x equals 1, and then I'd plug 1 back in to find the y's. And you'd find it would be at 1, 0, and 1, -4. All right, moving on. This is a tougher one. Yeah, let's do the horizontal tangents for this one. Let's go ahead and find dy dx. And again, horizontal tangent is when dy dx equals 0 or 0 over a number. So we're going to set our numerator equal to 0. Don't forget the product rule. Oh, Mr. Messner. Sorry, I'm sorry. Please, please. Don't you love it? I was like, don't forget the product rule. And then I messed up on the product rule. It happens all the time. All right. So I get dy dx, horizontal tangent. I'm going to set the numerator of dy dx equal to 0. Uh-oh. I have x's and y's. And the other ones that I did, I would just be able to solve for x or solve for y. Ideas. What do you think?
Find the y and plug it back to 0.
That's exactly right. Solve for a variable. This is a system. Here's my first equation. Here's my second equation. Okay? All my points that have to be horizontal tangents have to have this relationship. Solve for a variable. It does not matter what variable you solve for. Solve for the easier one that you're going to plug in. Then substitute that back into the original. Let's see what happens. I'll get x squared plus x times -2x plus -2x squared equals 0. X squared minus 2x squared plus 4x squared equals 0. Sorry, 27. I don't know why I'm putting 0. Three x squared equals 27. X squared equals 9. Plus or minus x equals 3, or x equals plus or minus 3. Fantastic. Now I want the x, y locations. Just like the last problem, you would think I take these x equals plus or minus 3s and plug it back in there. But actually, that wouldn't help me. It would help me a little bit. But let's look. When x is 3, I have 2 points. This x equals 3 and this x equals 3. Do both points when x equals 3 have a horizontal tangent? No, just this one down here, right? When x is negative 3, I have 2 points, this and this. However, only this one has the correct horizontal tangent. So if I plugged it into the original, it'd give me both points. But I only want one of the two. How can I distinguish between the two? Well, actually, we're not going to plug back into the original. What can I plug it back into, though? That guy. I've already plugged this into the original. Don't plug it again back into the original. Use this guy. Okay, so I'd have when x is positive 3, y would be negative 2 times positive 3, which is negative 6, giving me my first point, 3, negative 6, which is that correct one on the bottom of my ellipse. And then when x is negative 3, y is negative 2 times negative 3. So I'd have the point negative 3, positive 6, which is the other point towards the top and to the left of my ellipse, okay? So be careful. If you already plug in something into the original equation, don't use the original equation again. It would just give you some erroneous solutions, okay? And plug it back into what you used when you plugged it into the original equation. Don't plug into the original equation twice. And yes, there's concavity to these implicit equations. We can find an equation for the second derivative of this, and we can use it to look at the concavity. Let's go ahead and do it. Let's find dy dx. I'll just skip ahead in your program to that. Okay. Well, how do you find the second derivative? Take the derivative again. Nothing fancy, nothing crazy. Just take the derivative again. Now see how the notation works. Look. D times dy. That's how you get d squared y. D times y. Dx times dx. You should get dx quantity squared. However, the notation we use, which just makes it a little bit easier, is dx squared. Okay, now use the quotient rule. The derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Now this is great. This is the second derivative. However, almost always you will be asked to find the second derivative in terms of x and y. This doesn't just have x's and y's, this has a dy dx. I need to remove this dy dx. How do I remove it? I know what it's equal to. Substitute that in for dy dx. Now, it's probably good that you just stop there, but watch what I can do. I'm going to just keep going. I'm going to start simplifying. This is good. Check. We got it. Now I'm going to simplify. I got negative y. So negative times negative times negative. So this is still minus x squared over y squared. I'm going to give this a common denominator. I'm going to go negative y squared minus x squared over y minus y squared. Well, I'm going to, instead of divide by y squared, multiply by 1 over y squared. And I'm going to get negative y squared minus x squared over y cubed. And then I'm going to go ahead and factor out a negative 1. Y squared plus x squared over y cubed. And then I'm going to go ahead and put 25. Yep, that's it. 25. How did I get 25? The original equation is x squared plus y squared equals 25. While you're doing your homework, you will see that second derivatives will be simplified, sometimes kind of unbelievably, to something that looks so simple as that. You do not have to go this far, but it's cool to try. This is telling you that if your y is positive, we should be negative for our second derivative. A negative second derivative means concave down. Is y negative? You'd have a positive second derivative, concave up. Look at your circle. Look at it. Concave down when y is positive, concave up when y is negative. Thank you.